Our mornings, our homes, windows that open to the world. It shapes the skylines of a smarter, greener India, perfectly designed for modern life. In aircraft, it lifts ambition, light enough to soar, strong enough to protect. It powers our trains, connecting people, carrying dreams. It drives machines, ideas, industries, and impact. Aluminium extrusion is not just everywhere, it's everything you built upon. And at the heart of this movement stands LMI, trusted by over 50% of India's aluminium extruders. We mine, we source, we manufacture right here at home. This is Make in India, not in spirit, but in action. From north to south, from east to west, LMI's strength is nationwide. We go beyond manufacturing. We innovate. We elevate. We work with purpose, reducing carbon footprint, saving energy, driving sustainability for a carbon neutral India by 2070. And we give back, creating livelihoods, building skills, growing local economies. We don't just support India's growth, we power it. Driving innovation, driving a circular economy through sustainable aluminium extrusion. For a stronger, greener Viksit Bharat 2047. And now, the future unfolds. Welcome to Alumex, India's premier aluminium extrusion stage, where innovation meets opportunity, where industries connect, and the future is forged in metal. A global platform where governments, manufacturers, buyers, and chain makers come together to co-create real, lasting impact. 200 plus passionate exhibitors, 12,000 plus visitors, 100 plus meetings that shape the industry, 500 plus international buyers ready to partner with India's future. Alumex, where aluminium extrusion drives ambition, and our ambition drives a Viksit Bharat.
Hello. Welcome back, ladies and gentlemen, after the lunch. We have our next speaker over here, and she's from Henkel Adhesive Technologies. However, before we start her presentation, I would just request you to kindly wait for another 5-7 minutes because the lunch started a little late, and so everybody, I mean, most of the delegates are there in the luncheon area. We'll just let people to come in, finish up their lunch, and come back or in the conference hall, and then maybe we can start our presentation. It would be better. There's also a cabinet minister from Delhi government over there, and a short, a brief address is going on. Maybe that's why people are over there. So just allow us another 5-10 minutes. We'll shortly, start the session. Thank you.
Stewardship Initiative, and it's a pleasure to be able to talk to you today at ALEMAX India 2025. I am speaking to you from Melbourne in Australia, and so I'm sorry I didn't have the opportunity to be there with you in person, but I very much appreciated and felt honoured by the opportunity from ALEMAI to participate and contribute. I am going to be speaking about driving responsible production and sourcing in the global aluminium value chain, and speaking about the Aluminium Stewardship Initiative's ASI's work in space. So first to start about ASI as an organisation. We're a global multi-stakeholder initiative, and we're working to drive a sector-wide sustainability transformation for aluminium. We focus on the whole of the supply chain, the whole of the value chain, and within that, as we know, extrusion is a really key sector. But we're working from bauxite mining right through to downstream end-use sectors across a variety of aluminium uses. We're 10 years old this year. In 2025, we were incorporated back in 2015, and we are a registered charity. Our prime focus is on standard setting and certification, but we also work beyond certification, as we call it, to try and amplify our impact with broader stakeholders such as communities and Indigenous peoples. Our membership has been growing very steadily over the last 10 years, and we are getting closer to 400 members. And through our certification program, we have more than 500 certified facilities across 63 countries. In India, we have a range of members that are headquartered here, as you can see on the left, and on the right, a selection of some of our extrusion members globally. What we do is work to promote measurable and continual improvements in the key environmental, social and governance or ESG impacts of aluminium. We have a and that underpins the decisions that we make as companies. We have a standard setting and certification focus, but beyond that, we are also working to train and build capacity for members, auditors, and other stakeholders to implement these better practices. We collaborate through partnerships and with other organisations, including with Cross Recognition, to try and make sure that we can leverage what we're building in ASI and make sure that connects in with the huge amount of work that is happening in this space. And we also carry out data and research to measure and evaluate our and the sector and the value chain more broadly. So the certification program that we run is our flagship in many ways, and it has two parts, two standards. The first standard is our performance standard, and it sets out practices for sustainability and human rights principles that can be applied by companies right along the value chain. It sets out what's material, if there are specific things for bauxite miners or bauxite residue management, for example. But in general, we are looking to some consistent expectations through that value chain. So that's very much about the practices, what a company does. The chain of custody standard is then taking a link about that performance and creating a link then to the responsible sourcing of products or materials. And it does that by connecting certified suppliers and customers and accounting for material flow. By putting those two standards together, having certification against both, we're looking to provide recognisable assurance for responsible practices and responsible sourcing for the element value chain. The certification process is built for continuous improvement and moving towards compliance. And the assurance process, or the audits, are underpinned by an independent third-party audit that then comes to site to verify evidence, to interview, to inspect things, and then document their findings in Elemental. An audit report is submitted to ASI, and we carry out some quality control measures as well, mainly to make sure that we're seeing consistency of effort and rigour globally across the many sectors and places in which these audits are carried out. Once that oversight process is successfully concluded, ASI issues the certification and we update our public information accordingly. If there are any non-conformance areas, these should be addressed by the member through corrective action. And then there are also regular surveillance and recertification type audits, very similar to an ISO process, if that's something that you are familiar with. We aim to support our members in certification and more broadly. We run Elemental, which, as I said, manages those self-assessments, audits and reporting processes. It's a custom-built platform by ASI. We also have Educational, which is our learning platform online, where you can access a range of learning modules. We have regular webinars on key industry topics, usually 45 minutes long. And we also have a help desk and FAQs available. You can access direct support from our very knowledgeable team. And then connecting with peers is also an opportunity through working groups and similar, and that's a way to share knowledge and further build learning and capacity building. So as we know, and as you know even better than me, I'm sure, extrusion is a really key sector for impact. It feeds into infrastructure, transport, and renewable energy type applications. And so becoming part of the global effort to drive positive change in these supply chains is really critical for the broader sustainability transitions that we're trying to make as a world. And as a company, being part of ASI is an opportunity to improve performance and to scale up progress on key ESG issues by doing that collectively, by doing that as a sector as a whole. So with that, I'm going to hand over to Dango, who's going to talk a little bit more about ASI's work. But feel free to get in touch with me if you have any questions or would like to talk further about being part of the ASI community. Thank you very much.
Well, that was a quick message from Dr. Fiona Solomon, CEO, Aluminium Stewardship Initiative, who are also the knowledge partner for our conference. Next, we now start our technical discussion on anodizing of profiles. That's our new next session. And I would like to invite the first speaker of our session, Ms. Christina Acedo, Product Development, General Industry, Henkel Adhesive Technologies. Ms. Acedo is a seasoned professional with extensive experience in chemical industry. Can I have? It's okay. So sorry about that technical glitch. Hello. Perfect. Okay. Sorry about that technical glitch. also important that in our management team, we are almost 42%. It's not 50, but sooner or later it will come. Henkel, it's divided into different brands. We have our consumers brands and adhesive technologies. Maybe you are more used to or you are familiar with the consumer brands because we are taking care of this kind of products for the skincare, for the laundries, detergents. So maybe some of these brands, it sounds familiar to you depending on the country. For the other part, then the more industrial one, this is the adhesive technologies. We have Loctite, that is quite common from the adhesives, Teroson, Technomels, but keep it one name in your brain, which is Bonderite. Bonderite is our product, our brand for the metal pretreatment products. As I told you, we are in Henkel in 126 different countries, but we have some research and development centers, and here we are more than 2,500 people focused on development products and located all over the world. So now let's move in terms of sustainability. Of course, if we wanted to help to our customers to reach their goals in sustainability, first of all, we need to do it by our example. So we have our set goals in terms of sustainability, not only in the products that we are going to deliver, it's also when we are producing our products, our goals in sustainability too. So first of all, I mentioned that we are wanting to reduce our CO2 emission in more than 61%. We are reducing our water consumption during our productions. We are using for our products, we are investing and we are increasing the recycled plastic in our packaging. And also we are improving in other topics that I will talk later. So sustainability nowadays seems that it's a trending topic. Everybody talks about sustainability, but I would like to remark that sustainability it has a really long heritage in Henkel. So in 1993, we started to develop a product in order to reduce the temperature. So it's not nothing that nowadays we are talking about. We were working since too many years. But something that it was really peculiar is that in Germany, I don't remember the year, in 1959, I think, yes, in our company in Germany, they were starting to check the quality of the river, of the Rhine River, in order to prevent that all the chemicals, all the pollutions go into the water. So this is something that it's not nowadays a trending topic. This is something that is really in our NDA at Henkel. Of course, as I told you, we have our set goals in terms of sustainability. So for the 2030, we wanted to have an absolute reduction in the scope 1 and 2 by 42%. And in 2045, we wanted to have scope 1, 2, and 3 close to reducing 90%, so close to zero. This is why now idea is to new set zero target. And of course, for sustainability, it's always good to have good partners to help you to get your goals. So this is why we are present in leading some alliances. We are also setting in sustainability standards. And sustainability is not only something that Henkel says. We have been recognized by external ratings like EcoVadis, for example, and also we have been also awarded by different many leading customers like Novelli, BSH, Schneider, or Signify. And again, sustainablity, it's not only as a Henkel, we were also working in aluminum metal pretreatment, and this is why during these years we have different goals. In 1958, we started with a new cold bond. In 1980, we launched our first chrome-free product for the metal pretreatment aluminum in the automotive industry. In 1996, we have our first approved chrome-free customer in Qualicode, which is a quality labeling. In 1999, we introduced also a chrome-free product for the coil coating industry. In 2012, we have the Bonded 2040 that I will talk about this later. And in 24, we launched the alkaline edge temperature at lower degrees that also I will talk about later. And what is coming? It's a second generation of chrome-free products prepared for all the recycled aluminum that is increasing in our markets nowadays. So climate, it's quite important. We know that in the last years, the climate disasters increased per 5. All this happens. So this is why really we are focused in chemistry, but in process. We are not only thinking about chemistry. We think that we need to collaborate with our customers, not only providing good products in terms of low temperature or increase the efficiency of the product, or even less consumption. We also work with our customers in order to get reduce the stages of the processes, also to optimize the processes already existing in our customers, and also helps a lot the equipment and digitalizations to get all these goals. And I have the idea that it's better one image than 1,000 words. So let me introduce a short video about what Henkel thinks about sustainability. I hope it works.
It's crucial to respect the planet. It's our responsibility. And it's time for a rethink. It's time for us as pioneers to challenge the status quo.
Given our world's limited resources, it is essential to shift towards a circular economy by reusing and recycling existing materials while reducing consumption and waste.
Our solutions enable energy-saving and lighter designs to reduce emissions at every stage of the life cycle.
Safety for workers, consumers, and everyone along the value chain is of the highest priority to us. We proactively address chemicals under discussion and go beyond regulatory requirements.
Innovative processes can save water and recycle wastewater to address water scarcity and make every drop count.
We respect the planet.
We rethink design and processes.
We collaborate with customers to challenge the status quo.
Together with you, we create opportunities for innovations to actively shape a more sustainable future. It's time to respect the planet and to rethink design and processes.
Okay, so saying that, then let's go directly to the conversion coating and painting, and I will show you the different approach of the products from Henkel. As you know, in conversion coating, we can divide the process into steps. The part of pretreatment and the part of the conversion. For the pretreatment part, or for the process itself, what we wanted with a conversion coating is to improve the corrosion protection and to improve the adhesion of the painting. So this is the main topics that we wanted to get with the conversion. So what we have to do is to define the best pretreatment with the right steps. Also to select, because we have a big range of portfolio, to select the right products according to the material and to the necessity of our customer, and to define the right parameters that should be kept in order to keep the requirements from the customer, to keep also the quality. Of course, all our pretreatments in conversion can be applied by immersion, by spray, or by cascade. So this is the typical different lines that we can find in a conversion as a treatment. So for the pretreatment, the target is to clean the material and to leave it free of any kind of pollutants and activate the surface in order to later on give a right conversion layer. So what we wanted to do, or through an acid or through an alkaline plus acid, depending on the customer, we will do this this pretreatment part, in order, as I mentioned, to keep it as cleaner as possible for the conversion topic. In the conversion, we have different types. This is true that in the last years, the typical or the normal process, it was a chrome 6 process, which improved the corrosion resistance and the paint adhesion. These kind of products are liquid products, and you can use it in all the pretreatments. And it's based on chromate, fluorides, and accelerator. But as Henkel, and due to the fact that sustainability it's our main concern, we have alternatives to chrome 6. This is true that chromating it's quite reliable, has color, so it's really easy to differentiate when the material is treated or not, because you can see color on the surface. You don't need a DA rinse previous the conversion, and also it has a really good protection if you don't paint. This is all the pros, but unfortunately, chrome 6 has a really high concern. High concern in terms of toxicity for the environmental and also for the workers. And also you need a pretreatment in a wastewater pretreatment, because you need to reduce this chrome 6 to chrome 3. So which are the Henkel alternatives? And also, and I don't want to forget that point, is that it's really required too many rinses, a lot of water. So it's a really step that you requires a lot of water consumption. So which are the alternatives of Henkel to this chrome 6 pretreatment lines? We have different proposals. The first proposal, that is our traditional chrome-free, that it has been in the market for more than 20 years, with a lot of square meters treated all over the world. And we have other ones that I explain later. But let's go for the traditional one. In the traditional one can be applied in a layout of, for example, this is a horizontal or a spray vertical line. You started with an alkaline cleaning, rinses, the oxidation, of course, of the surface, and then it's ready to conversion coating and rinse. This is true that this rinse before the conversion needs to be with the best quality as possible. So if it's possible, DA water, much better. Or if not maximum than 100 microsiemens. So this is like a Henkel solution. It's an example of a line for an alkaline degreasing. We have different products, or by acid as Bonderite CAK 2105 or the 24600 that I will talk later. Acid etching, and of course this conversion coating, or our Bonderite 483031 or our Bonderite 400. Both products are approved by Qualicoat, also approved by GSB. It works at really low temperature and low concentration compared with chrome 6, which is working at a high concentration. We are talking about that the layer of this product is milligram per square meter, so it's really a low conversion coating, and can be also applied by IPNR, that I explain you later what is the IPNR system. So in that case, I would like to introduce this new product, this new launch coming from last year, which is the Bonderite CAK 24600. It's a traditional alkaline degreaser, alkaline etching degreaser. In the traditional step, this kind of products, it's a mixture between soda, potassium, and other additives. with this new product, we are able to etch the material at the same time, as you can see, time 2 minutes, keeping the same rates, but we are able to decrease the temperature. So instead of the traditional ones that can work at 40 degrees, to achieve exactly the same performance with a lower concentration, we can work 10 degrees less. So this means a really reduction in terms of energy, and this is a lot of savings per square meter of the bath in terms of money. Another solution to Chrome 6, it's our alternative of Bonderite MMT 2040. This is the new generation of the Chrome-free products. Again, all these kind of products needs to be, it's mandatory that should be approved by GSB and Qualicode. It's really a robust Chrome-free, and they have a lot of water savings that I will show you in a diagram just right now. As you can see here, there are different layouts. I don't know if I can. No. Okay. You have different layouts to convert a plan from Chrome 6 to 2040. In a Chrome 6, as you can see, it's required the typical pre-treatment part. This is something that we cannot skip. And for the Chrome 6, we need rinses before, and of course, definitely and mandatory, a lot of rinses after all to keep the quality of the material. When we change from Chrome 6 to Chrome free, to the traditional Chrome free, we can switch easily Chrome 6 by Chrome free, but we need always a DI rinse, one or two, if maybe one is more than enough, depending on the quantity of water that we can provide, but needs a mandatory DI rinse before. Later can be because the two products that I show you can work with or without rinse. So we can skip the last rinse. But if we change to 2040, we have like another concept. It's a concept that we can use it as a conversion metal pretreatment product, but can be worked also as a cleaner coater. What means a cleaner coater? Means that we can etch and we can treat at the same time. So we are etching the material and we are creating like a self-control conversion coating. So it means that we can establish two stages with the same product, skipping the rinse in between because we are talking about the same product. Later on, some rinses, and that's all. So from the top till the end, we will have our material treated with a good quality and of course with less investment, with less water consumption, a reduction of 30% more or less, and of course an increase in productivity because we have less stages. And last but not last, this is our APNR system. What is an APNR system? It's an adhesion promoter, no rinse. It's an equipment that can be easily installed in an existing customer. At the end of the line, it's secreting like a mist. You are mixing the product in the same time, so it's free of pollutants, and then you can ensure that your material they will be free of pollutant. It's always fresh. It goes directly to the material, and it's only a dust. It's a mist. So then the wastewater treatment, it's not a quantity of water, so you can save a lot of water. This is really useful, for example, for customers that are working with Chrome 6 and they wanted to change to a non-Chrome 6 system. Why it's important? Because to get rid of Chrome 6, if you've been working with Chrome 6 for so many years, the Chrome 6 in these Chrome-free products, 1 ppm of Chrome, it's a pollutant. So you can damage the non-chromium product, the process itself. So if you install this APNR at the end of the system, you create the non-chromium without any problem and any fear that the material will be contaminated by the Chrome 6. We have more than 100 units installed and working perfectly. And as I told you, can be an option for all the customers that want to switch from a Chrome 6 technology to a non-Chrome 6 technology with a minimum invest, because it's really easy to install and it's not really required any modification in the line, because it goes directly at the end of the line. This is the setup of what is needed. It's only a couple of pumps in order to mix the products, and then you create this mist. And again, as an image, it's better than all my words. I will set up a short video that will show you how it works, this APNR. These are the benefits that I already mentioned. Of course, it's a water reduction because it's not a real rinse and it's not a real bath, it's only a mist. The quality, it's always constant because there's no pollution and you are mixing in place. And of course, it's plug and play, as I tell you. It's very easy to install, and the parameters are keeping always permanent because you have all the equipment and all the pumps, and you can follow the process with an equipment and digitalization.
Introducing Bonderite Adhesion Promoter No Rinse, the next generation in metal pre-treat. Engineered for excellence, Bonderite APNR delivers unmatched corrosion protection and ensures optimal paint adhesion. Its compact, modular design makes installation simple and seamless, saving time, space, and resources. Bonderite APNR supports sustainable manufacturing with non-chrome options, certified by Qualicoat and GSP products for performance you trust. Designed with sustainability in mind, Bonderite APNR significantly reduces chemicals, water, and waste, enabling safer handling of your product. Enjoy consistent, high-quality results without the need for constant supervision. Bonderite APNR keeps your line running smoothly with our own fresh chemistry. Are you ready to revolutionize your metal pre-treatment process? Discover the power of Bonderite APNR, where innovation meets simplicity.
Okay, so here is an example of a real existing product who installed the APNR and all the pumps and all the equipment to control everything in alkaline etching and acid etching in a customer take 2, and that was after some months of treatment. That was the results directly from the customer, that he was able to save 20% in wastewater treatment. They reduced the energy between 15 and 20 with the previous process, and they reduced also the water consumption of the total plant. And another example for the same, another customer that introduced the APNR in the system, in their line, with all the pumps, and again, they reduced the chemicals, also the water, the wastewater treatment, because in that case was a Chrome 6 changing to Chrome 6 to Chrome free. So this is why the wastewater treatment decreased so much. Also the cleaning and maintenance of the equipment, also the disposal, and also the quality improves a lot after this treatment. And this is an example of what is installed at the end of the line, this APNR system. And the last topic, let's talk about anodizing and sustainability, our most innovative product for the anodizing. What we wanted, or our challenge in anodizing, and not only in anodizing, in most of our products, it's try to get the same quality, but with products more sustainability in terms of reducing time or reducing temperature during the pre-treatment time, and if it's possible to give to our customers energy savings or less water consumption. So this is the aim. So we will be focused on etching, anodizing, and sealing. But let me talk about cleaning. Cleaning is the most important step in a metal pretreatment, no matter if it's conversion coating, no matter if it's steel, if it's another surface treatment. The first step is cleaning, and cleaning should be done in the right way. You can have the better conversion product or the better anodizing line, but if you don't clean the material properly, you will face sooner or later problems. So what I wanted to show you with this slide is that at Henkel we are working, we are specialists in cleaning, and we are working to develop cleaners at lower temperature than the normal ones that we have nowadays, in order to have less energy consumption, if it's possible, of course, to reduce the carbon footprint, lower water consumption, and eco-friendly, VOC-free. Saying that, let's go to the etching. For the etching, I would like to introduce the Bonderite CAK 62350. This is a product aimed to get the E6 finishing to the material. And the aim or the benefit of these products compared with the traditional that are in the market, it's that it's really easy to rinse off this product. Remember that it's a really high alkaline bath, so it's really sticky. So with this new improvement of the product, it's really easy to clean it. You avoid over-etching, and as you clean it easily, you avoid also the carryover. There's a small video that can show you how it works. There are traditional long life etching and the new development. I'm not going to tell you who is who, but you recognize easily as soon as the product will be rinsed. It's only for a few seconds, and here is the magic. One of them they have residues on the surface, and the other one there's no any residues on the surface. So it's really easy to clean. Now let's move to the anodizing additive. Everybody knows that anodizing, if you wanted a good quality of anodizing, you must keep the temperature between 80 or 20 degrees. In theory, it's not possible to create a good quality of porous, not able to anodize over these 20 degrees. With this additive, this Bonderite MAD 2008, we achieve 24 degrees. What means to anodize at 24 degrees? A lot of savings for our customers in terms of, basically, in terms of energy. Why? But of course, keeping in mind that we will keep the quality of the porous, because there's a reduction in aluminum dissolution. You increase the bath life. You have also lesser consumption in sulfuric acid, can be faster, and of course, instead an anodizing process, as you know, it's a exothermic reaction. So it's always trying to increase the temperature. This is why you need a chiller in order to keep it at 20 degrees. So the chiller will be needed, of course, you cannot skip it, but it's not the same to cool down until 24 that to cool down at 20. So this is the great benefit of this new additive. And also the new thing is that it's a quality approval, which is a certificate from an external. So it means that you can use it because it's proven and it's guaranteed. And last but not last, this is my last product, it's on sealing. The Bonderite MAD 11204. This is a medium temperature sealing. With medium, we are talking about 85 degrees. The normal sealing, we have three different types of sealing. Hot sealing, which means a bath over 96 degrees. Medium temperature sealing, which is this new development at 85 degrees. And cold sealing, which is this kind of product based on nickel that is at room temperature. In this case, we are free of nickel, so it's a really good quality of product. But instead of 96, we are able to seal at 85. This is true that there are some products in the market, and even we have also some products are for sealing at 85 degrees in our portfolio. But the innovative thing from that product compared with other ones is that you can skip the last final rinse, so you can save water. As soon as the material is sealed, you can discharge and you can sell it as soon as possible. So, and even it has a shorter sealing times compared with the traditional medium temperature sealing. So it means that you reduce the consumption in energy, the CO2 emissions, and of course the water usage. So this is all from my side. Here is the one of the key contacts that if you have any doubt, you can contact with us. And if you have any question, it would be nice, and I'm glad to answer any doubt that you have. Thank you very much for your attention. Thank you, Ms. Christina, for your presentation. Do we have any questions from the floor for Ms. Sidhu? Okay, fine. So I think, yeah, presentation was pretty good and clear. So, but anyhow, Henkel has got a stall in the exhibition area. So in case you would like to get in touch with the representatives from the company on any queries, so please do get in touch with them. Their number displayed over the screen, or you can get in touch with us. We can also connect you. Thank you so much, and a small vote of thanks from our side, ma'am. The next speaker we have with us, Dr. Bidut Kumar Manna, Vice President R&D and QC with GTZ India Private Limited. Dr. Manna is a seasoned expert in chemistry with a PhD from Jadavpur University and over 32 years of research and leadership experience in industrial chemistry. His expertise spans electroplating and aluminium treatment chemicals, steel mill formulation, organic synthesis, emulsion, polymerization, and nanotechnology. Currently serving as Vice President R&D and Quality Control at GTZ India Private Limited. He leads a multidisciplinary team of over 25 scientists and chemists. Dr. Manna has authored multiple research papers and holds two international patents in US and EU, reflecting his significant contribution to applied chemical innovation. I would like to invite Dr. Manna on the stage for his presentation. Yeah.
Good afternoon, everybody. Up and down. Mainly, I will be presenting three topics. One is anodizing, next is the post-treatment of anodizing, that is sealing, then treatment for period to powder coating. So let's start with the anodizing fundamentals. So anodizing is a electrochemical process that produces anodic coating, mainly aluminum oxide or corrosion resistivity. So as it is the electrochemical process, so for electrochemical reaction all are required, that is one anode, cathode, electrolyte and DC current. So this is the anodic reaction. In anode, first aluminum oxidized to aluminum 3 by electrochemical reaction. Then it combines with water from the electrolyte and produce aluminum oxide plus hydrogen ion, and as it is anodic process, then it releases electron, 6 electron. This is the electrode ion balance. This is the equation 2. Then there is a reduction in cathode. Hydrogen ion becomes hydrogen gas. That is equation number 3. As a hydrogen gas is produced in anodic reaction, so in anodic plant, good exhaust system or ventilation system is required because hydrogen is flammable, so it has to be removed from the anodizing area. So net reaction, this is a net reaction, means combining of 2 and equation 2 and 3. This is a final reaction that aluminum plus water, it will produce aluminum oxide, that is anodic coating, and hydrogen. And this is the pictorial picture of anodic coating, how it looks like. There will be a porous coating and some barrier coating. Cell is like, and after that, this pore is to be sealed, which is the method called sealing of this aluminum anodized chemical. So what is the benefit of anodic coating? Major is the main is the corrosion resistivity, then increase the hardness, and another important is resistance to heat resistance, because aluminum melting point is only 660 degree and aluminum oxide is 207 degree, means it is 3.1 times higher in heat resistivity. And last is the aluminum oxide is the second hardest material after diamond, so it will increase the hardness also. This is the factor that affecting the anodic coating. There is the electrolyte, that is sulfuric acid. Optimum range is 160 plus minus 10. Maximum is 200, but you can increase the concentration even after 200 by using anodic, some additive for anodizing. And for hard anodizing, it require, for temperature it is 21 plus 1 degree, maximum is 24. And if you increase the temperature, then this green color conductivity will increase, condensity will also increase, coating thickness will also increase. But major that protective value will be decreased. That's why this is the optimum temperature density. Time depends on thickness, but there are two thumb rule for time measurement. One is rule 312, that time require in minutes equal to micron desire into 3.12 divided by current density in ampere per dm square. Another rule is time required in minute to get desired meals of coating. One means is 25.4 micron into 720 divided by current density in feet per ampere per feet square. So current density is this range 1.2 to 3. Slower, if it is slower, then flame growth will be less and time will be more. So this is the optimum range. Aluminum content in the electrolyte is also important. If aluminum content is more than the maximum range, then higher voltage will be required. It will not desirable. Then heat production will be heat generation will be more, and the coating roughness or coating aesthetic look will be less. Then chloride. Chloride is detrimental for any corrosion resistance coating. That same logic is applicable to anodizing coating also. The maximum tolerance is 100 mg or 100 ppm. So for anodizing DM water, chloride water is desirable. Now I will be discussing type of anodizing. There are three types: type 1, type 2, type 3. The major variation of this type is the coating thickness in micron. Type 1 is the least, and type 3 is the highest coating. And another is the variation in the electrolyte. Type 1 is electrolyte formic acid is used, and type 2 is sulfuric acid. Type 3 is also sulfuric acid with lower temperature and higher voltage. So application is different. Major application is the type 2 for general decorative and functional agricultural purpose. Now the classification is two type. One is natural non-dye type, and another is dye type. The total anodizing process is the pre-treatment, then main anodizing. After that, post-treatment includes coloring, electrocoloring, and sealing. So this is the pre-treatment synopsis for one natural anodizing, acid decreasing, caustic decreasing, dismatting, and then sealing, post-treatment. Satin finish anodizing, one extra process is there for satining finish after dismatting, then another dismatting. So before anodizing, all type of pre-treatment is dismatting. Similarly, bright anodizing, non-H type alkaline cleaner, then followed by chemical binding, then dismatting, then anodizing. So for color anodizing, electrocoloring, possible dyeing, and immersion chemical dyeing. But after anodizing and coloring, sealing is must, and every variety there is a sealing. That is the last and final treatment of anodic coating. Suitability of aluminum and its alloy. There are different types of alloy that can be anodized, but mostly popular is 6000 series and 7000 series. Even 6063 is versatile use and main use in this anodizing purpose. It is the alloy of silicon and magnesium. Now I will be discussing the troubleshooting in anodizing. First one is insufficient decreasing. It is visible after etching and binding, and this is because of non-uniform decreasing. The causes is poor decreasing solution or practices. Temperature is too low, residual oil of the bath is high, then the tolerance limit. So what is the remedy? The solution, if the old decreasing bath, then you have to replace with the fresh one. And if there is any changes in any parameter of the system, then you have to compare with the other system. Here there is a popular type known as track, which is essential for cleaning track with temperature, agitation, chemical concentration, and time. If you reduce one any of the parameter, then you have to compensate by increasing the other parameter to get the sufficient decreasing. Staining, it is visible after etching and coloring. Main issue is etching, higher etching solution dyes on part during transfer. If the time gap between etching and ringing is more, then this could happen. And wrong etch solution and etch temperature is too high. So for remedy, there improve the time lag between etching and ringing, and temperature should not be greater than 600 degrees. Okay. Anodizing burn. Burn, it is visible after anodizing. This type of pattern, round shape pattern in bright anodizing, it is because of higher current density than the normal. Higher current density is required because four movement of electrolyte occurs than four electrical contact. So current density has to be reduced to get rid of anodic burn, and electrical contact has to be improved. Chloride corrosion. Chloride, it can be visible after anodizing. Peat formed on all surface. Chloride corrosion. So in how it is remedied, so use chloride rich bath, chloride water in the anodizing bath, and take care for any dog in and anodizing bath from the area state. Color variation, it is visible after coloring. Main fault is alloy inconsistency defined in anodizing parameter. If the anodic coating is not uniform, then color variation will be there because of the depth of the anodizing coating and incorrect dyeing condition, labeling and pH and other things. So you have to optimize this to get in consistency in color. White spots, it is visible after electrolytic coloring, dyeing and sealing. There are varieties of white spot and variety of many reasons for that depending on the shape and mainly depending on the shape and the location of the white spot. Main pore changing, pore dismatting. Another is a mold formation both in the rinsing bath as well as dyeing bath. So how to improve it? Rinse can be improved by flowing water, excess flowing of water and time, and for fungi growth, the rinsing tank water should be changed or any fungicide or algaecide can be added. Caging. Caging is cracking if hairline crack from the anodic coating. If there is certain temperature change or any shape change, there is a crack because the thermal expansion of aluminum and aluminum oxide is not the same. Always the thermal expansion of metal is more. So there will be, if there is any deformation or any certain temperature change, there will be a trace and that crack will be there to release the trace. So thermal shock has to be reduced. Reduce the thermal shock. So say if hot ceiling is there, so from anodizing to hot ceiling temperature difference is around 80 degree. So you reduce the you incorporate one extra step, that is first chill in 60 to 70 degree, then go to hot ceiling condition. So there will be less thermal shock and there will be no cracking or crazing and no bending or deformation after anodizing. Whatever it is required, it has to be done before anodizing. Now sealing failure. So this is the sealing depending on the color, intensity of the color, this is the variety. So for copper sealing 0 or 1 grade is required. Sealing dye spot test is not removing from the sealed area. This is the problem. How to correct it? Check the sealing wax temperature, solution and sealing. If it is deviated, then adjust it and check the contamination level of sealing bath. Some phosphate, silicate and bivalent metal are increased this impurity are hindering the sealing quality. So that needs to be reduced to get proper sealing. So now I will be discussing in details for different type of sealing and their mechanism, etc. Why sealing is required? It improves the corrosion resistivity, enhance aesthetic, reduce dye leaching quantities if it is dyed after anodizing, then preventing the ingress of corrosive material and contamination into the anodizing layer. So this is the sealing parameter, that temperature, solution pH, solution composition, immersion time, and contamination control of contaminant level in the sealing bath. Phosphate is the most detrimental impurities and maximum limit is only 5 mg per liter. So this is the pictorial presentation of mechanism of sealing. Initially, first layer is without any only anode layer, then hydrated product filled to the pore of the mouth. Then it is usually progressed towards the interior of the hole, and there is some hydrated alumina gel. Then the hydrated alumina gel become dehydrated and formation of asimilar bohide structure, and it will then seal the pore and complete the coating sealing system. Now type of sealing depending on the temperature of application. There are three types: cold or room temperature sealing, mid temperature sealing, and hot sealing. Again, that cold sealing is mainly divided in two or rather three parts based on composition. First is nickel chloride base, second is nickel acetate base, and third type the newly developed chemical that is nickel free. Initially, it was based on lithium, but due to the introduction of lithium battery, as lithium is becoming costlier, then magnesium has been attempted, because magnesium is in the periodic table. If you consider the periodic table, it is just the diagonally opposite to lithium. So most of the properties of both lithium and magnesium will be similar. That's why magnesium-based nickel-free sealing, both for cold and mid temperature, is gradually becoming popular. Another sealing is there, that is zirconium-based. So mid temperature sealing also divided into nickel-free as nickel salt, and hot temperature sealing, it is totally free of metal and based on organic. Now the sealing parameter of different type of sealing. I will not discuss the parameter. It is known. It is already known. I will discuss only the mechanistic part, that is chemical reaction and sealing process. Cold sealing, there are four reactions. First one is the aluminum plus chlorine is aluminum chloride, which is insoluble and fill the pore. Second is nickel plus OH minus nickel hydroxide, that is also insoluble and seal the pore. And third is aluminum. Hydrated aluminum becomes initially it is hydrated, then it becomes aluminum oxide, hydrated aluminum oxide. It will also seal the pore. And then aluminum hydroxide, full hydrolysis of aluminum oxide, that is also sealing the pore. Here the four mechanism is observed. That's why the cold sealing is the fastest stage. Only 1 minute is required per micron average. Mid temperature sealing is only two mechanisms: nickel hydroxide formation as well as aluminum hydration or boehmite structure formation. So it is a little slower than cold temperature sealing. And hot temperature sealing, only one mechanism is there, that is hydration of aluminum oxide and boehmite structure formation. So that's why only hot sealing is slower, around 2 to 3 minutes per micron. Another hot sealing is also done after cold sealing. That is time is not so important. Only 2 to 5 minutes is required for the post cold sealing treatment. Then different study of SAME and EDX for sealing processes. First one is that only anodic coating. So aluminum, oxygen, all aluminum coating is elemental composition is found. We have selected the four spot, and the analysis result of the four spot has been reported here. Then last right side is the image, same image, and EDX analysis of elemental composition after complete sealing. Here you can find nickel and chloride as one of the composition for the, it is coming from the cold sealing chemical. Now mid temperature sealing. Here that left side is same and EDX picture of the half sealing. Means if 10 minutes is required for the complete sealing, it is after 5 minutes. So here only nickel is found in the composition as elemental composition, and for the right hand slide it is the same picture and composition analysis of the pooled seal. You can find from the nickel content that after pool sealing nickel content has been increased. It is around 4.2 and half sealing it is around 2 to 2.2. That means that the nickel hydroxide or nickel is also getting involved in the sealing process as metallic hydroxide. Now the hot sealing. It is also similar type of medium temperature as that picture is concerned. First picture of the same is the half sealing stage, and the second is the full sealing stage. Here there is no metal, so you can see from the carbon, which is the representative organic content in the half sealing. Carbon is not uniform, and it is still average is still less, and for full sealing carbon is everywhere, and the content is also higher than the half sealing. Testing of sealing quality, there are mainly four tests. One is dye spot test as per ISO 2143, mass loss test, that is the formic acid and phosphoric acid test, that is ISO 3210, then admission test. Aluminum oxide is inert, so it is not so conducting with aluminum, so aluminum conductivity will be less, and that is measurement of admittance. It is less than 20 microsiemens, and one is a visual test. So I have completed polynote system, more or less all parameter and details. Then I will be going to the polycoat system, that is the pre-treatment or conversion coating on aluminum prior to powder coating. This is the process flow diagram. Initially, pre-treatment surface preparation, degreasing, etching or dismatting or 3-in-1 system. Then the pre-treatment, that is the conversion coating. It is basically three types. One is hexavalent based, hexavalent chromium based. Again it is depending on the color, it is three types. Green, which is less commonly used and mainly for military precision, is the highest coating thickness or weight is highest in green. Then yellow iridescent, it is the most popular one. Another is that is the intermediate coating thickness, and the colorless is the lowest coating thickness. But yellow iridescent is popular, and what should I use? Trivalent, it is based on chromium, trivalent chromium, almost colorless, and then compre, one is the colorless, and the newly developed yellow. As colorless is very difficult to identify whether it is coated, conversion coated or not, then the yellow color, which is similar to hexavalent yellow, it is easily traceable whether it is coated or non-coated, and it helps operator for right identification. That's why yellow color is beneficial to operator. It is operator operationally. After pre-treatment, powder coating, application, curing and cooling. So surface preparation for pre-treatment, etching, one in simple etching, just acid etching, then double tank acid etching plus acid etching. Then there are dual etching, alkaline etching, acid etching, alkaline etching, followed by acid etching. So this is the different type of etching condition, and etching degree as per code specification. For general purpose, 1 gram per meter square etching methodology is required, and for C-side test, it can be 2 gram per meter square. So now I will be discussing COM 6 conversion coating, that is yellow. This chemical is mainly of two types depending on the component of the system. One is single component and another is double component, A and B. One is for initial bath preparation and second one B component is for bath maintenance. So this is the special parameter mainly pH is similar 1.8 to 2.2. Appliance temperature is room temperature. Curing time maybe natural curing or some 60-degree temperature. PMT can be applied for quick drying. Dipping time is 2 to 6 minutes, and for double it is 3 to 9 minutes. And we have done different coating weight at different dipping temperature, which for single component 2 to 6, and coating weight is also matching with our normal specification 600 to 1200. And similarly double component it is dipping time is 3 to 9, and coating point is usually time is increasing, coating also increasing, but it is within the specification range. Now I will be discuss elaborately on roast compliant non-conversion coating of chemical. There are again two types. One is foam free, which is free of foam sticks, and another is foam free. Foam free is again divided into two, colorless and yellow. First picture is the chemicals appearance. Trivalent chromium is green in color. Foam free colorless is chemical is also colorless. Foam free yellow is reddish color. Then the bottom part is the picture of coated panel from foam free and foam free. It is normally colorless natural color, but in picture it is coming little color. It is not like so. But foam yellow, it is giving the exact color. It is totally yellow in nature, so that operator can identify whether it is conversion coated or not. So ease of traceability. Foam free conversion coating parameter. This bath consumption is little higher, 10 to 30, optimum is 20. pH is little higher than extravalent, 3.5 to 4. Temperature is room temperature. Curing temperature is 60 to 80. Dipping time 1.3, and the coating weight range is 200 to 400. And we have done different time for dipping, and this is the coating variation. Lower the time, lower is the coating. And it is Qualicoat approved, approval number is A160. This means all testing after powder coating is passed. That is cupping test, bending test, all test after powder coating as per Qualicoat specification is passed. Foam free. So that is colorless, is little lower consumption than the yellow color. Yellow color is just the double of colorless coating, because thickness of this coating is also higher. pH is similar. Application temperature is room temperature. Curing temperature is around 60 to 80 degree. Dipping time varies. For colorless, as coating weight is less, so 2 to 4 minutes, and for yellow it is 4 to 8 minutes. The coating range is for colorless 75 to 150 mg per meter square, and for yellow it is little higher, 300 to 700. It is also Qualicoat approved. Qualicoat approval number is A159, and so it also passes all the Qualicoat parameter after powder coating. Now, what is the advantage of foam free? It is environment friendly, and roast, ELD, WHOI, REACH, and OSHA compliant, satisfactory corrosion resistance similar to foam containing product, compatible with paint, powder coat, easy wash treatment, higher heat resistance. So this is the hazard pictogram. If you consider extravalent, all type of hazard is there, and it is also carcinogenic. And in trivalent chromium, only corrosive and harmful, and foam free is also similar, but trichrome is the intermediate, as there are some paper which indicate that foam 3 on prolonged exposure to UV light can be converted to hexavalent. That's why trivalent is the intermediate step and foam 3 is the final step to get ROS compliant coating. This is same idea study of foam 3 clear. This is first left side is the same picture of the coating before SST, salt spray hours. And this is the EDA spectrum of for elemental composition. We have selected 3 areas and the composition is given there. So before salt spray, you just check the chromium content. It is average 7 and 0.7%, and after SST 5% was last, it become average 4. So titanium is washing out after salt spray, and titanium is the major contributor to the salt spray hours. This is first slide is first same picture and EDA spectrum of comb pre-yellow before SST, and right one is the same picture and EDA spectrogram of comb pre-yellow after salt spray, that is 5% white rust. Here is also the main component of comb pre-yellow is organic and titanium. Before salt spray, you can find the higher content of carbon as well as titanium. After salt spray, both carbon, that is the representative of organic chemical, that is also getting reduced, and titanium also reduced. Comb pre conversion coating is very suitable and can replace hexavalent chromium and trivalent both. So different option has been attempted for comb pre formulation, but titanium, zirconium or mixture of both are found suitable, and it can replace both hexavalent and tri-comb passivation. So I have not mentioned any of our product in our presentation, but GTZ has a whole range of aluminum anodizing as well as conversion coating product. So Mr. Abhijit only is looking after the marketing of aluminum chemical. You can reach him by this mobile number, or you can scan this to get him. And we have also stall in this. You can meet him in the stall also. Thank you. The now presentation is over and it is open for discussion.
Thank you, Dr. Vidyut, for your time and for the presentation. We would like to present a small token of thanks from the ALEMAI community to you, please. Next, I would like to call Mr. Sabai Ahmed, Sales Manager at Marks, with a strong professional background in electrical engineering and pump systems. He has dedicated his career for developing and implementing sustainable solutions. Over the years, Mr. Ahmed has worked extensively on international environments, focusing on continuous improvement through Six Sigma practices. At Marks, he plays a key role in driving sales and building client partnerships across diverse markets. Mr. Ahmed.
Hello everyone. My name is Amit Svai. I'm from company Max. I'm the sales manager and sales engineer at Max. And I would want to thank you for your numerous presence here. And I would like to present to you our next generation smart container. And I hope after the presentation you will have an idea about the importance of a good and intelligence control of the temperature in the extrusion process in the container. So the first questions to ask is how to achieve an isothermal, a uniform isothermal stress into the container while extruding. To achieve that, it is important to have uniform product quality, a greater producibility thanks to constant heating conversion in the container, so homogeneous temperature in the container is very important. And also a greater productivity, the tank, and also a longer service life for container and the die. With a good temperature curve in the container, you will have less stress in your container. So that's why we developed temperature controlled containers. I'll present now some key elements of a smart temperature control in a container. The first is the temperature measurement, two, the heat elements, and three, the control system. First of all, the temperature measurement. You can see here. You can see here a picture of a drawing of a container, and you see here many zones: zone 1, zone 2, zone 3, and zone 4. This is a heating system with four zones. And you can see here in each zone there's an insert for thermocouples with two measuring points. You see here zone number 1. There's measuring point number 1, measuring point number 2, and the same for the other zones. In the middle, we have here a thermocouple. With this thermocouple, we can ensure that the temperature is in the mantle doesn't get too high. So it's here to say that the temperature recording in the container is very important, also for the health of the container and also for the good quality of the end product. The temperature measurement can be made with a thermocouple. There's a one measuring point thermocouples and two measuring points thermocouples. You can see here the first measuring point is here, and the second one is here. This version of the thermocouple has here like a sort of a bayonet or thread, so that it can be installed to the mantle of the container. We have also this kind of thermocouples that they don't have any bayonet, so they can be used in the case when no machining on the holder of the container is allowed. So you can make here a groove into the container and route the thermocouples outside of the container. You can see that also here. The second key element are the heating elements. So I'm presenting now the Marx HPC cartridges. These are the high-performance heating cartridges. We can achieve with these heating cartridges up to 3 zones per cartridge. With this kind of cartridges, you have an individual definition of the values in each zone of this cartridge. And it's also possible with this cartridge to have a custom-made solution for every heating system and for every requirement of the customer. These are some possible heating zones that can be reached with our heating cartridges. You have here one zone heating, you can get also 2-zone heating, one ring at the die side and one ring on the stem side. You can have also upper and lower shell, and also 6 zones here with rings and upper and lower shells. Here you can see a standard 4-zone heating system. You have an unheated area in the middle of the container. You have zone 1, 2, 3, and 4. And this is the new heating system which we call next generation. Also here you have a variable heating zone in the middle. So this is really a physical unheated zone which in the container. So here you can see also our heating, a 3-zone heating cartridge. You can see it clear. 1 zone, 2 zone, or 3, or let's say 1 zone, zone 2, and zone 3. So you can have here on the die side the first zone, which is the upper shell. The second zone is the lower shell at the die side. And we have zone number 4 at the stem side and zone number 3 in the middle. And zone 1 and zone 3 are short and powerful zones in both on the die side and on the stem side. They are very useful during the production. The middle zone, this is zone number 2. It's longer and designed with less power, so it can be shut off during the production. Because while producing, the billet has a high temperature, and this temperature is put to the container, and also there is a process temperature that is also put in the container. So we have in this area like a belly temperature belly, and in this area the temperature is almost 50 degrees higher than the rest of the container. So we shut this zone off because we don't need the temperature in this zone anymore during production. And this is a typically and most used heating zone layout of the next generation system, including 4 zones. Zone number 1, 2, 3, and 4. Zone number 1 and 2 are like on the die side, Zone 1 representing the upper shell, and Zone 2 representing the lower shell. And we know that the temperature in this area of the tool site is high during the process. And the temperature goes always from bottom to top. So we have to ensure that the temperature here gets lower. So we reduce the power of this zone, or we shut it completely off. It depends on the temperature at the moment, in the moment of extruding. So we can save here a lot of energy with decreasing the power put through the control system. Zone number 4, it prevents from the cooling of the front size while producing, because on this side there's no isolation, nothing, just air, and the container loses a lot of temperature on this side. So we need this zone to keep this part of the container also under the set point temperature of the heat of the extrusion temperature. Zone number 3, this is the biggest zone. It has less power, and it is almost completely shut off during production because of the temperature. There is a high temperature here in the middle of the container. So we can understand from all this as an optimal heating placement of the heating zones is very important for maximum efficiency, for an effective use of energy, and for high performance. And it's also very important for a good health of the container. Because if you have an uncontrolled container, you have temperature differences in your container, and that leads to temperature shocks, and that would have a very negative effect on the container. So it can be cracked, or the mantle would be soft with the time. And with this solution, you maintain also all key advantages for modern extrusion requirements. Another very important, let's say, philosophy of heating system is, from our point of view, that the heating system should be arranged on the outside edge of the second third of the container diameter in this area here. So the heating system is always located in the mantle, and in the case of large containers with a diameter of 2 to 3 meters, in the medium liner would be nearly here in this, but never near to the inner liner. So we have here the heating in the mantle, and on the right side we have the heating near the inner liner. Why we do that? Because the inner liner is the fastest part, or the fastest part of the container that reaches the required temperature because of the process energy introduced, and also because of the hot billet that it put inside the container. So arranging the cartridges directly into the inner liner in in this case here, causes the system to switch off immediately because the thermocouple records in this area, oh, the temperature is high, I have to shut off. So when you shut off here the temperature, the mantle will still cold. And you will have here big temperature differences between the inner liner and the mantle, so that you have here temperature shocks that could lead to crack in the container. The other aspect is when you put the heating cartridges pores near the inner liner, you have here a smaller diameter. So the machining here will make the container much weaker than machining them in a big diameter. So that's why, from our point of view, this is not a good way good situation to install the heating system. What also very important for a smart heating system are our max wick connector. With this connector, is it easy and fast to make a connection from the power cable for power supply to the container for frequent changes, let's say one time in 6 months. And the other advantage of this solution is that you will never be able to switch the cable connection and the heating zones, because everything is arranged here. Here will come the power cables, and they go directly to this connection with silver plates. We have also the compact connection. This is also very easy and reliable, and also here we have an advantage that no permutation can be occurred while connecting the heating system. The third very important part is the control system, because without a smart control system, there's no smart heating. So everything must match together and be smart. This is one of our containers with a control system cabinet. And here you can see the control cabinet for the visualization for the monitoring of the temperature in the container. So the result of a smart heating system is we can have a smart container, and it is also applicable to every kind of containers from 500 kilograms to 100 tons. And you have also a homogeneous temperature curve in the container. And due to all smart systems we have, like I've shown before, the compact connector and the control system and the quick connector, you have a smart problem-free solution for the operation in the extrusion industry. So there's also an option, which is every container can be retrofit and to the new smart system, next generation, with everything what belongs to, like the double thermocouples with full temperature recording, You can also get a cooling air regulation if you want to cool the container. And you have also a data monitoring for analyzing the data after the production. Thank you very much for your attention, and I wish you a nice evening.
Thank you so much, Mr. Ahmed. Are there any questions from the audience? That would be. Thank you so much. We are very delighted to have you at Alumex with us and would like to present you with a small token. Without further ado, guys, it's my privilege to introduce Dr. Mayor, Managing Director of WEFA Group. He's a distinguished mechanical engineer with a PhD in material science and has held leadership roles across multiple organizations. He brings with him extensive international experience, having served as MD at WEFA. And also with his deep expertise and global perspective, Dr. Mayo continues to drive innovation and growth success across WEFA's worldwide operations. Please welcome Dr. Mayo on stage, please.
So here we go. Some technical issues. Yeah, welcome to my presentation on productivity improvement with coated dies on a special example with one of our esteemed customers. And I want to guide you through some optimization we have made together with use of so-called cartridge dies. Here you can see, is that working? Yeah, this is wafer. We are a manufacturer of aluminum extrusion dies for many years, more than 50 years experience. Wafer has 6 locations in Germany, Switzerland, Czech Republic, and the US. Around 300 employees worldwide and global customer base, so also here in India. And the production volume around 25,000 dies a year. Dies we do are from very small dies, 40 millimeter only, up to bigger dies with 600 millimeter size. So we had an experience from a very old die from 2013. That was only a single cavity die on a 6-inch press, die size 200. In 2019, we try to increase productivity. So what we do, we include, we increase the number of strands into two cavity, use a slightly bigger die, and then in 2022, we even try to include a 4-cavity application in a much bigger die on a bigger press. It's a 9-inch press. And also here we try to incorporate 4 little cartridges. So usually you have a big die, and there we try to use individual units, inserts, so-called cartridges. So that was a productivity increase we tried to achieve from 2019 into 22 by doubling the number of strands. And also, that's not the only one. We try to also use coated cartridge inserts. So these inserts here, which I show you, that's easier. So these inserts are not only cartridges, they are also CVD coated. So first of all, what is a cartridge? In die making, there's die makers below us that's not very, inserts are very well known, but cartridges in fact is inserted in an individual special holder. Then the high production consistency with minimal dimensional variation is possible, because you can imagine it is a taper execution, and these tapered cartridges are clamped against or back to the backer, so it's totally stable inside the holder. So therefore, if this is the mandrel, there is only a minimum deflection, so you can run very precise profiles. Yeah, very small tolerance are possible with this type of design. Yeah, very small mandrel is always also possible. And then what does the CVD coating do? CVD coating stands for chemical vapor deposition. It's a special treatment of the die after the production. So instead of nitriding, which would be 5, 6, 7 times renitride, we would just do one single CVD coating
So all the materials of the coating, they're going to be evaporized, and on the hot tool surface, there will build up layer by layer into a very hard, almost 2,000 or 3,000 Vickers hard coating. Of course, longer service life is one of the aims with the coating, but also the design of the bearing. We can optimize a better surface finish. So also we can not only the coating, but in combination with the bearing design, we are able to get a better profile surface. Higher extrusion speeds are achievable due to the reduced friction of the coating. If you see exit temperatures, usually they can be reduced by minus 10 degrees C. This can either go into higher speed or even better surface finish. Both can be used. Minimum maintenance efforts. So I was explaining if you have 5 to 6 times renitriding, the dye needs to get out of the dye, needs to be caustic, so put into caustic soda. We can eliminate this. The dyes can be used without any caustic treatment, so you even can leave aluminum in the dye and run and run and run. Last but not least, also with the CVD, there is smallest tolerances possible. You can imagine if you have nitriding, that will also come from two sides into a mandrel, and with only 10 microns thick coating that can be eliminated. So what happened after we included these cartridges in 2022? Of course, everything was perfect. Only we had so-called streak lines. They were observed after anodizing. This was not seen before, and also created a problem to the customer. Here you can see it a little bit more in detail. That is something which was not acceptable after anodizing. So what I had to do a root cause analysis. The project approach was to simulate afterwards, use the simulation software, design optimization, then of course extrusion optimization, and a practical application after. So what was the root cause? Here we find out that the structure of the streaking could be detected only on one side of the profile. It was always the outer parts of the profile, and the position was on the outer parts of all the 4 cartridges. So it was only here, 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 and here. So here again, that was the streaks. And for the stability reasons, the profile positioning in the die holder is more on the outside of the billets. I mean, you can imagine these cartridges, they need a little bit more space outside, so it's not an optimum anymore. So you need to get cartridges a little bit wider and outside of the holder. So our objection or observation was that billet skin could have had a grain strice, and their grain strice structure could have been coarse, and so-called dirt and oxides could move into the profile sections and lead to an uneven grain formation, which then created these streaks we've seen. So also we tried to simulate the results afterwards. This was done by Q-Form software. So we have Q-Form also here in the show. Welcome. So what we tried to have before extrusion, and then we have seen that billet skin, even after only 40% of the entire billet length of 1.2 meter was already sucked into the system, and remaining billet skin enters into the die stack here. In a further step, the position of the streaking was simulated, so you could see here even some of the streaks we were able to simulate by the efforts of the software. Also again here a little bit in a closer objection then could be reproduced. The simulation highlighted the exact same location which we have seen during extrusion. So, of course, we tried to optimize the design, and we had a couple of ideas. Also, we incorporated and used software simulation to detect and to see what we done from an engineering standpoint. The die and the holder was adjusted, so in the first step, we try to reduce the maximum material inlet, and then in a second step, we even separated the inlet. So instead of one big feeder, we created small feeders, and that helped tremendously for optimizing the design and to avoid these streaks. Based on these results, we could the separation here, we could see this also. That only after 350 millimeter of the remaining billet skin, so we could reduce the effect by that. So after 350 millimeter frame, the butt length was even still long, with 350 still too long. So we had we also were forced to do something during extrusion, to work with the extruder. So what did we do? We adapted extrusion parameter. So what did help is that we decreased the container temperature also, overall container, so not only part of it, so also the entire container temperature, reduced it by 30 kelvins, and we also reduced the billet length by 200 millimeter. So what happened that we see that only 120 millimeters left for creating the skin entering into the die stack. So tremendous success also working together with extruders. Practical application, of course, then in we discussed in a partnership base with the extrusion people, the die team there, and of course the simulation results were verified. So you see here there were no streaks anymore, so that helped. And the design adjustment was implemented into the new die holder, of course. And what we also did, we examined the butt. So we did some cross-section analysis, and we also could find that there were no residues anymore. So what we did also in the end, we recommended the extruder to increase their butt length a little bit by only 5 millimeter. You see 5 millimeter is not much, but helps tremendously to reduce the billet skin inlet. That's always something we recommend, not to save on extrusion and better have a longer billet butt in the end to also create a better surface quality in the profile. Yeah, so you see, that was the overall success story. Was to conclude, finally, is that we found the cause of the surface defect and could have increased the productivity. Of course, the project showed the importance of a combination of a suitable die design, verification, with simulation and the optimum setting of the extrusion parameter, always together in a close collaboration, die maker and the extrusion plant. Last but not least, the close collaboration can reduce the number of trials drastically. So my recommendation to the extruders sitting in the audience, please keep the die maker in the loop, and then of course our mutual target is to reduce the number of dry trials by a close cooperation. Yeah, would thank you not only you as the audience, but also my co-writers, Dr. Beckett, Louis Rauscher, and Jan Swoboda from our UEFA Czech team, and also our customer, Grupa Kenti from Poland. Thank you for your attention.
Thank you so much for your patience at the beginning and for this presentation. We would just like to thank you for coming to Alumex all the way and would like to present a small token of thanks. Thank you. We're almost concluding the day with one last presentation. And with pleasure, I would like to welcome Mr. Ivan, Regional Sales Director at Qform Group. With over 10 years of experience in metal forming and processes, Mr. Ivan has played a key role in advancing innovative technology for alloy modification and industrial applications. His deep expertise and leadership in sales and business development continues to strengthen Qform's global presence in the aluminum industry. Welcome to Alumex India.
So this microphone is Hello everyone. So this day I want to show you some presentation concerning the extrusion simulation and capabilities of simulation software. Now, virtually, with Qform software, we can simulate almost all production chain of the extrusion process per se. And let's start from the scratch. But really, let me introduce Qform a little bit. So, Qform software is used for simulation of various number of metal forming processes, starting from forging, wheel rolling, and ending with extrusion, which is the main topic. And concerning the extrusion, we successfully participated in almost all the international benchmark tests since 2005. And also I would say that during the last benchmark test, we were the best. For example, considering the welding quality prediction, which was one of the tests provided by the authors of the experiment. So now, sorry. So let's start from sketch. Every project of extrusion starts from the profile drawing. And once you start, you need to consider potential thermal shrinkage as well as potential deformation. After that, you look into the container that you have, the press that you have, and then you check what you can do about the ports. About the ports and how you will control the flow of your design. Using a pre-chamber, using some internal features of the design for pores, thinking about what the cooling areas, some feeding areas that you need to provide for the particular design, so on and so forth. So the designing stages can be divided into several parts. We start from the 2D contours, Then we need to follow and create some parametric model of that tooling set. And finally, finish the design and send it to simulation. This is typically how the process of the designing of new die looks like when you have a simulation software. With a special solution from Qform, it's called Qform Extrusion Die Designer. It is possible to automatically adjust bearings or pre-chamber because we have a direct interface between two software, between the simulation software itself as well as CAD that we are developing too. But recently, we start to look forward to the optimization not only of pre-chamber and the bearings, but also looking into optimization of ports, because simply every port is like a mini container which fills different parts of the profile. So it will be obviously the most influential part. So what you can see on the screen is the following. There is some contour of the welding chamber that was produced by a real die producer, and the simulation as well as real results was great. And the green contour is now provided by the software even for the simulation. So what was done in order to get almost like ideal contouring even without the simulation? We analyzed around 150 simulations with box-shaped profiles and just find, using some machine learning procedure, some equation that makes it possible to predict some coefficient using the offset contour of the profile to produce some welding chamber. And this is what you can observe on a screen. Now it's still in the development stage, but we are looking forward to release this feature in a new version. So this is how it works. Here, as you can see, the result is not absolutely ideal, but what you need to also get into consideration that here bearings absolutely flat. So only using force optimization, it is possible to achieve a very good flow, and it works. So now, we will talk about some basics of Qform UK simulation, and there is very typical approach for metal-forming simulations. Typically, a Lagrange model is used. The all nodes are moved along the field velocity distribution. The mesh is needed to be remeshed very often, and this process is kind of time-consuming, to say the least, and not that stable. That's why Qform, historically, we were using a combined Lagrange approach, which provides the possibility to simulate process much faster. For example, there is a comparison between a standard Lagrange approach with the standard default approach that Qform now uses. And if you will look, you see that the result is completely the same. That's why we will use our approach, our current approach, because the simulation time is more than 10 times smaller. What else? Another thing which is important, which makes the simulation accurate, that we have so-called thermally and mechanically coupled tests, which provides the possibility to get a very accurate result. So what I mean? If we will consider some particular extrusion case where the consideration of the tool deformation will not be taken into account at all, the result will be completely different if you will look at the experiment result and the result from the left side. While we will use the default approach that Qform uses with deformable die, where not only any deviation or displacement of the core during the extrusion, but also the formation of so-called relief choke angles are considered. So this is why we can achieve a very good results considering flow simulation. There are some examples of kind of complicated color profile, but this result we typically check during so-called profile flow simulation. That is a standard, but sometimes the extrusion process is a little bit more complicated, and we need to dive deeper to the details. Here, we need to analyze so-called cold billet length simulations, another type of analysis that we can perform with the simulation software. So what we have here, there is some case study with central feeding areas, and basically this was the problem. So what happened? This is the profile flow results, where we can consider this result to be relatively okay. The profile front end looks okay, and the result is like this. So you can notice that on the right picture there is so-called waving or buckling of the central wall, which was not really a good solution for the customer. And if we will analyze the velocity deviation or velocities during the cold process, we can see that the second and the third stage, which refers to the middle stage and end stage of the extrusion, we can see a tremendous effect on the velocity. This central wall starts to flow faster and faster, which also can be checked considering the change of the temperature field, which you can see here. Or, if we will look into the graphs, you can see that the central point starts to be faster and faster somewhere between the middle stage. This is exactly when these defects start to appear. Another example of the angle, simple angle profile, but here the reasons were a little bit different. Here we also can consider 2 points, point 1 and point 2, but if we will look at them, there is not so much difference considering the temperature. So here, not the temperature. The temperature is not the reason for the waving. The reason is a complete redistribution of the flow, where once the disc length or button length decreases to some particular extent, where this full recombination of the flow starts to appear. This is what we can see, that at the third stage, at the end, when the disc length is about 30 millimeters, we can see a very high increase in the velocities. Flow is not the whole story about the simulation analysis. Of course, if you will extrude the profile successfully, it's already a good result, but what's about a tool life? There is some example from one of our customer, Compass. And here you can observe some cracks all around the bridges. There are several approaches how we can predict it, and one of these is checking of the plastic zones all around the webs. Once you see it, it's a very direct indicator that something is wrong and you need to redesign the tool. Another example from extruder company from Dubai, Gulf Extrusion. Here we can see for semi-hollow profile. And what is happening here? Console parts have a very great area of plastic deformation, as you can see here. And this is the very reason why it breaks. And they extruded this core with a profile, which is not a good outcome, to say the least. Another approach is to check the stress state under the webs, because you not only can expect the crack appearance on the console parts of tongues because of high tongue ratio, but also under the webs. Very common. Unfortunately, here almost every time we can have some plastic deformation under the webs because of very high tensile stresses. And we have a special criterion, and once there is some critical value of the criterion achieved, using some post-processor analysis, we can find these areas and say that there will be cracks. So the exact matching of these results that you can see on this photo. Another example of heat sink die. So what happens? If we will look deeper into the results analysis, we found really two big problems. One is displacement, and another one is plastic deformation. Heat sink dies and heat sink designs are very unstable, and it's not that easy to create a good heat sink. It's very typical that they can break. And here you can see that with the simulation software, it's possible to predict it beforehand. You will do a very time-consuming trial. Another thing that after the simulation, after your technology is well done, you can export your profile to a special interface in a new version where you can check the dimensions of the profile. And there will be like a table where you can see the deviation of the profile according to the drawing and the profiles that you can have after the total information. So now let's consider several typical extrusion defects that can occur during the extrusion. The first one is so-called underfilling defect. So here you can see the profile with a very different thickness in different areas of this profile. And here, unexpectedly, they end up with some additional coal right in the center of the thick mass of the profile, which is not a good result at all. And if you look deeper, we will find the reason under a particular bridge. Okay, and so here there are two solutions. You can try to optimize the tool just based on the opinion of die corrector, but if you will do the correction of the bridge in that sense that you can make your stability of the course too bad, you can even break the tool. That's why during the optimization it's very good to check it beforehand using a simulation software before you will modify the tool and break it. There are some additional examples of this defect. So red area shows the underfilling. Stricken lines. We have already discussed this topic this day during the WEFA report. And there are typically two main reasons for stricken. Let's consider at least two. The first one is called thermal streaking or thermal streaks, which appears due to variation of the strain rate and temperature all along particular areas of the profile. Typical areas are T-section or areas where we have screw ports, so there is some variation of the section itself. And here you can see with the different screw bosses and thickness nearby them, you can see a different formation of the streaks. One big and two smaller streaks near screw bosses. Another example, and another case. Like in the previous case it was presented, the reason it looks so is the billet skin. So this is a two-cavity design, and here you can see that during the extrusion, in the central port, there are a lot of contaminated, oxidized areas of the billet starts to flow, which is the reason, or could be one of the reasons that led to this defect. So it is possible to analyze your technology from different perspectives. Another thing which is very important when you try to provide the customer in automotive sector or where the structural profile is required is the welding quality issue. The welding quality is very important, and existing criterion appears not to be enough. So if we will just consider that this weld is okay, this one is not okay, we will be like too strict to these two positions. And we separated it into three categories. So welded, it could be structurally welded and mechanically welded. For structural, when we have structural welding quality, it's okay for automotive, and for the profiles which requires a very high surface quality. Mechanical welding is okay only in case when this surface will not be visible for the eye. So it also be okay. In absence of welding, it's basically not welded stage, which is not that easy sometimes to achieve, but it happens. So there is some case study with a simple tube where you can see a welding line all along the extrusion. And here we can find the position of this welded line, and also the values of the criterion. And where you can see that the value is lower than 1, which means that this weld it doesn't have a structural welding. So here we can see what typically can be done when you start to optimize design. Typically, you will try to provide more pressure under the web, but the issue is that if you will do it too much, you can break the die or your profile will be out of tolerances. So always when you do an optimization, you need to look at the design and at the outcomes of this optimization from different perspectives. Because if you will do this correction, maybe it will be very difficult to do it again. And you will need to recreate the die or measure the die from the very beginning. So after this correction, you can observe that the result is much better. That is why there is no any visible welding line on the surface. Another example, just to make it faster, here you can see the area where we can see a visible interface between two different streams, so basically between two different ports that form this profile and form this weld. And this area is very bad. This is what we really can call mechanical welding. And here you can see all the welds which doesn't have a good quality, were marked, and it has a very good correlation with the software. Scrap. Scrap issue is very important for extruders and for the die makers when they have a competition before they get the order, because typically the amount of scrap considering so-called charge weld is mostly dependent on the die design, the welding chamber, the height of the welding blank height. And the question of the optimization of these parameters is very important. So here you can see the visualization of so-called seam lengths, or transversal seam lengths, and the stop mark value. And this part is typically discarded, so basically this is a scrap. Here you can see some picture. Depending on different extruded lengths, you can see that the new and old material will be presented in a different percentage all along the sections. So basically, you can, once you have an order, optimize the charge weld until it will be minimized to a particular value, because it will provide you a very huge economic effect when you will extrude the profile with smaller scrap. Another part of the scrap is a so-called billet skin contamination due to oxidized layer. It really depends on the quality of the billets. So it's very good to have a good supplier, or to have a good laboratory to check before you will start the extrusion. What is the skin layer thickness? Maybe there's some problem with this particular production. So here you can see that depending on the button lengths, we will observe a very different picture how the oxidized layer starts to appear inside. Typically we have two main movements of this layer. Once appears somewhere to the center at the bottom part of the billet, and another one goes somewhere nearby the dead metal zones in the container and in the die. If we will stop the extrusion at this button length, it will be okay. There will be no any additional scrap value. But if we will consider the continuation of the extrusion process, and you will see the picture like this, and your required button length will be 40, you will have an additional scrap value. That is why you can optimize design or the button length or the billet length, and will not extrude the scrap. There are some examples from some of our colleagues from Italy, from researchers and scientists. So this is a so-called coring defect, which you can see here, which correlates well with this data. Very simple example of the rod extrusion. If we will rotate this rod, we can see that some part of this profile is separated from each other and can even be extracted from it. If we will look in the extrusion, like in a section, we can find this internal, let's say, cylinder of the scrap inside. and also can predict it using a simulation. Another thing, just to sum it up, once we did a good project with dye and everything looks great, it's not the whole story. Why? Because the dimensions of the profile, especially when we're talking about the hard dailies like 682 and so on, there could be another challenge, cooling process. Here, there is a graph which we can use in order to understand what quenching window or operational window for the quenching process looks like. Here you can see the following story. If we will extrude too fast, we will end up with a huge distortion of the profile, like this. So it will be bended, and the shape will not be that great. Another problem, if we will not cool profile fast enough, at this time we will have reduced mechanical properties. So basically it will look like this. And in order to implement the software, we did several tests with existing articles available in the scientific literature. There was a very interesting experiment from Hamburg University, if I'm not mistaken. Was very interesting experiment, and we tried to simulate it. The aim of the simulation and the articles that we eventually created based on this experiment was to identify how good our heat transfer coefficient is, because here it has a tremendous and crucial importance on the simulation results. And here you can see that once we finish the project and customized our new heat transfer coefficient, the result is matching the reality considering the cooling rate. So it means that potentially we can virtually simulate the quenching process to predict the cooling rate, the needed cooling rate, and potentially the deformation of the profile with the accurately predicted cooling rate. In order to set up such type of simulation, you will need to do the following. The first thing is to create the model for the quenching station. This is a cooling station where you can position all the sprayers, provide some parameters for the nozzles, assign some additional geometrical parameters, so on and so forth, and then you need to set up the simulation. The initial data for this simulation will be the section of the profile, which you can see here. This is the profile right after the simulation, and that is why you can see some non-uniformity of the temperature distribution. And here it is important. In the software, yes, it is possible to simulate with uniform temperature, but you can guess that it may be not the best idea. Once you have simulated the extrusion process, you can set up the quenching station parameters like flow rate in a particular nozzle or pressure, which typically fully determines the intensity of the cooling. Then you simulate the quenching process, checking if the cooling process is good enough, considering the displacement of the profile, the thickness variation, or whatever is interested, maybe even grain size. And then, if it is not good, you start to do some optimization. You increase or reduce some pressure in some nozzles and get a result. And finally, you can check and compare different setups considering the overall X and Z displacement. And finally, you can create some graphs for the characterization of the deformation, like twisting angle of the profile, as you can see, was optimized and became much lower compared with the first red curve. Mechanical properties also can be predicted using the software. Once we have a good cooling rate, we will not end up with a very huge non-uniformity of the mechanical properties distribution inside the profile. If it will be not that good, you will have some non-uniformity, like in the second case. Also, you can check the section itself after the process. And there is some additional example which like was done on an advanced level. It's not really the usual part of the software and the design so far, because it will require a very good cooperation between extruder, die maker, and maybe us sometimes. So here there is a different setups of the quenching station where different nozzle areas were turned off or turned on, different pressures and flow rates were used, or were not used at all. Here you can see different regions of the profile where microstructure samples and eventually BSD diagrams were obtained. And here you can see the results. So here you can see three different conditions of cooling and the prediction of so-called PCG or peripheral coarse grain layer, which will be obviously different depending on the cooling rate. And here you can see different cooling rate graphs. At the top, M8, M10, and M19 just refers to different cooling rates. M19 is only on air cooling, and here you can see that the recrystallized grain layer is the biggest here, which we can observe here as well in result. Between M8 and M10 there were no any big difference, that's why I used only one picture. While on air cooling you can see a completely different structure considering the thickness of the fibrous grains and PCG layer. It's a 6005 LA, that's why this layer is so big. If it will be 6082, I will not expect such a variation, but it's also possible. So this is the result. So in conclusion, the application in industry is wide now. It's not only useful for the die designer who can use it for these applications. So basically, if they want to start a new project, they can optimize the profile velocity, check the dimensions of the profile. But it's not the whole story. If they have a good configuration, like it was presented in the last presentation, they can do much more with the simulation possibilities. And extruders, they are always interested in temperature velocity mode, in productivity optimization. Because if you will find the limit of the extrusion speed using the simulation software, it's a good thing to know beforehand you start the extrusion. Profile quality control, so all the defects that we discussed today can be predicted. Scrap control is very important. Quenching finally is available. And for both sides, die life control and charge well control is very important. So basically that's it. This is what I wanted to show you concerning the simulation capabilities that we currently have. So we can start basically from scratch, create the design, and end up with an analysis of the quenched and cooled section. Thank you for your time.
Thank you, Mr. Ivan, for walking us through very patiently. And thank you for attending Alumex again. Thank you for being a very patient audience today. We have an entertainment session arranged for everybody after a tea break. I would request everybody to proceed to the entertainment hall in the same passage. Thank you so much. We'll see you tomorrow.